So we were discussing representation of C of x, and in particular we were discussing what are called cyclic representations. Okay, so C of x, and so we were discussing the following proposition. So, okay. So first we proved the following. We proved in the last class that if mu is a measure, I mean, given any mu, yeah. So, given any finite measure, mu on x. So this x is contained in C. Okay, I mean it's a metric space, but for convenience, we assume that it's contained in C. Okay. Okay. Any finite measure, then we define pi mu from C of x to L2 mu, B of L2 mu by pi mu of f acting on any g is just fg. It's just the product of g. So then we proved that this is a proper representation. This pi mu is a star representation. That means it's a homomorphism. Okay, star. That is pi mu is a unital star homomorphism from C of x into B of L2. So this is a C star algebra. That's a C star. C of x is C star algebra, and we have this satisfy pi of 1 is 1. Pi of fg is pi of f. Pi mu of fg is pi mu of f times pi mu, just the operator product, and pi mu of f bar pi mu of f star is pi mu of f bar. So the star operation in C of x is just taking bar. Okay. So this is the unital representation. Conversely, we proved the converse. Conversely, given, and this pi mu is a cyclic representation. So that's also, pi mu is cyclic. That is, their x is a cyclic vector. Their x is a cyclic vector. G0 is a, if you take the function, constant function 1, then pi of f, pi mu of f, G0, you just take the span and closure of this is a whole of L2. It is just clear because C of x is dense in L2 mu. It is dense in all of L2 mu, in particular in L2 mu. Conversely, we also proved the converse, and we use Rees representation theorem. Conversely, if pi is a representation, pi is from C of x to B of h for some h is cyclic. So notice that we are not actually assuming h is separable. In all throughout this course, whenever we talk about Hilbert space is separable. But the separability follows here because C of x sits inside. C of x acts as operators, and also acting on the cyclic vector, C of x sits inside, maybe not 1, 1, but C of x sits inside the Hilbert space also. I mean, this f going to f of xi naught. Xi naught is the cyclic vector, it sits like this. Okay, so that gives a dense subspace. I mean, well, you have to consider the topology, but you will see that that will force the h to be separable. Okay? H will be separable. I mean, the topology in C of x and the way topology, the C of x sits as C of x in B of h. I mean, that the norm is preserved. See, this map is f going to pi mu g is contractive. I mean, it may not be, it may not, I mean, this is a homomorphism, so it's contractive. It may not be, what is it? It may not be isometric, but it's contractive. So I mean, sometimes it is isometric also, but for L infinity is isometric. We haven't proved it. We prove it now. So for in general, it's contractive, but F sits inside H also. You take any F in C of X, then you can embed this as F G naught in H. Okay, if you have a cyclic thing. And well, I don't want to go through this. You can check. This is okay. This is you write this assignment. Okay, this is the assignment. You think about it. If you don't get it, we will discuss it. Okay, so assignment. That is pi from C of X to B of H is cyclic, but this will force it to be. I mean, this is actually there is nothing. I will not give that. I mean, because we have there is no assignment because we have already proved that this looks like pi mu for some mu. Then we know that. I mean, then we know that it is actually how it sits inside and it is dense there. Okay, but this is true for in general for any separable C-star algebra. This is true. If you have any separable C-star algebra, then when you embed it, when you have a cyclic representation, then that Hilbert space has to be separable. That's a different fact. Let us not discuss it now. Okay, so the same fact makes H separable. But here, conversely, if we have a representation pi, which is cyclic, then we use Greece representation, then there exists a finite measure mu on X such that pi is unitarily equivalent to pi mu. So pi is unitarily equivalent to pi mu. Okay, that is, there exists a unitary u from H to L2 mu such that u star pi u is equal to pi. Okay. Okay. Or you can write it as put a F here. Okay. So this is the converse. The third thing we wanted to prove is we were proving this and we stopped. Okay. Pi mu, there exists a representation. Pi mu extends to L infinity. C of X, I mean, C of X, all functions are bounded. So it is embedded, it's contained in L infinity. But the L infinity norm may be smaller because you are taking essential supremum. So with respect to that measure, so the norm may decrease. So the pi mu, this pi mu extends to a representation of L infinity. So there exists a representation. There exists a pi tilde mu from. I mean, this is given a measure. So let me write it as a separate proposition. We fix our notation. Given a measure mu on X, we denote pi mu the multiplication representation. Okay, so there exists a representation. There exists an isometric representation. Pi mu tilde. The original pi mu may not be isometric, but this pi mu tilde is isometric. Okay, so even if you consider C of X, if you consider the L infinity norm, it is isometric. But then the L infinity norm is smaller than the C of X norm. I mean, the infinity norm, uniform norm on the uniform norm. Pi mu from L infinity X mu to L2 X mu. Okay, such that pi mu tilde restricted to C of X is equal to pi tilde, pi mu. Okay. Further, if we have a sequence Fn, maybe for L infinity we will use a different notation. The sequence phi n contained in L infinity, L infinity of X mu, okay, such that supremum of norm of phi n infinity is less than infinity. Okay, they are uniformly bounded, and phi n converges to phi almost everywhere. Then pi tilde mu of this phi n converges to pi tilde mu of this phi strongly. You know what is the strong convergence? That is pi tilde mu phi n g going to pi tilde mu phi n g for all g. It's a point-wise convergence. It's not norm convergence, it's point-wise convergence in L2. Okay, for all g. Okay. So this is what we want to prove. So the extension is just again the multiplication repetitions. Okay. So for phi in L infinity mu, define pi mu tilde phi acting on any g equal to again phi. I mean, you can multiply. These are all. I mean, you can multiply point-wise, but still consider the equivalence class. Okay. So there is a small confusion, but that does not really create a confusion. L infinity are not really functions. They are functions considered up to equivalence class. Okay? And similarly, L2 is also equivalence class. They are, it is just but then it makes sense. You can multiply this. I mean, you can talk about multiplication, point-wise multiplication. Then they take the equivalence class, and that is well defined. Okay, so we can talk about this for all G. So this is a. I mean, we have already proved that it is less than the L infinity norm. So this is certainly true. This is a representation and it's contractive. I want to prove that it's actually isometric. Okay, so we want to prove it's isometric. So we want to prove pi mu phi, the operator norm, this tilde is same as norm of phi infinity. Okay. That's right. So how do you prove that? So clearly, so first thing is we know that it is normal. So pi mu tilde phi. I mean, it's a star representation. This star is just phi bar. I mean, it's a pi mu tilde phi bar. So it commutes. So it commutes. I mean, this is a representation of L infinity, which is commutative. L infinity is commutative. Multiplication is commutative. So this is also commutative. So it's normal. Pi mu tilde is normal. Okay. So norm of pi mu tilde phi is equal to the spectral radius of pi mu tilde phi. This operator, right? So we have to compute the spectrum. So as I said, if you have functions, if you have continuous function, then the spectrum is, I mean, the spectrum is just the range of that function. If you have a function, continuous function, f is c of x, then sigma of f is just the range of this, range of f, which is just f of x. Is this clear to everyone? Some f is invertible if and only if f does not vanish. Okay. So we want to consider f minus lambda is invertible, so it should not vanish. So lambda should not be in the range of f. That's what it means by it's not invertible. So if it is invertible. So if it is invertible, it has to be in the range of that. It's the other way. So, but then for L infinity is slightly different because we are considering the, I mean, L infinity. So the claim is the following. Lambda. So we want to calculate the supremum of this. So so how do we say that is the, so we want to prove this. To prove this, it is enough to prove, I mean, we want to prove this. The norm of pi mu is same as norm of the L infinity norm. Okay, so for that it is enough to prove that I'll come to this. So to prove this, to prove star, you want to prove that that the norm is same. It's enough to prove sigma of pi mu phi, sigma of pi mu phi tilde, which is the multiplication representation. That is equal to, I mean, we want to prove that its range is, it's not the range, it is just the, I mean, it is just the difference between something in the range should be less than epsilon for all of them. The measure of that should be greater than 0. So let me write that. See, first let us claim the following. Claim. We'll go one by one. Lambda is in the spectrum of sigma of pi mu tilde phi. Okay. That is equivalent to saying lambda, that is equivalent to saying mu is the measure. Mu of this set. Mu of this phi minus phi of omega minus lambda. All those omega such that phi of minus omega lambda is less than epsilon, is greater than 0 for all epsilon. Okay. So lambda is in the spectrum of this operator, this multiplication operator pi mu phi, if and only if mu of this set, phi of omega minus lambda, all those omega, this set has to be greater than 0 for all epsilon. Okay. So first let us prove this. So lambda is in sigma of this, sigma of whatever. That is equivalent to saying lambda is an approximate eigenvalue. We proved it in the last class. If something is in the spectrum, in finite dimension, something is in spectrum if and only if it's an eigenvalue. So here it is an approximate eigenvalue. Okay? So lambda is in the spectrum. This implies there exists Gn with norm Gn, L2 norm equal to 1. And I'm just writing the definition of approximate eigenvalue such that pi mu tilde Gn, pi mu tilde phi, sorry. Phi Gn minus lambda Gn. Okay, this norm 2 goes to 0. Okay, as n goes to infinity. Okay. Okay, so this is just equal to integral phi minus lambda, phi minus lambda Gn, okay, phi minus lambda Gn whole square d mu goes to 0. The point is, claim is, I mean, this should imply that that set is greater, that set has measure greater than 0. If mu of, if there exists an epsilon, I mean, if mu of this set, omega, such that phi minus lambda phi of omega minus lambda of lambda is less than epsilon is equal to 0 for some epsilon naught. We want to prove that this is equal to this is greater than 0 for all epsilon. Suppose if this is equal to 0 for some epsilon naught, okay, then this should not happen. That's what I want to say. Then this integral phi minus lambda square gn square d mu is equal to integral. You can take the integral over phi minus lambda greater than or equal to epsilon naught, plus you can take the integral over phi minus lambda less than or equal to epsilon naught. Okay, but then this measure is 0, so that integral does not exist. So this is just greater than or equal to, that is 0. So this is just greater than or equal to epsilon naught times integral of gn square mod gn square dv. But this is equal to 1, so this is equal to epsilon naught. So this does not go to 0. Okay, so this does not go to 0. Okay, so this is a contradiction. So this is true. Okay, for all epsilon greater than 0, mu of this phi minus lambda less than epsilon naught. This set goes to 0. This set is greater than 0. Measure of this set is greater than 0. Okay. Conversely, suppose we want to prove the equivalence of the claim. Suppose mu of omega such that phi minus lambda less than epsilon. So there is no epsilon. Epsilon naught is greater than 0 for all epsilon. Okay, then we want to prove that it's lambda is an approximate eigenvalue. So take Gn to be 1 of this set, omega such that phi minus lambda less than epsilon, divided by the measure of that. I mean, you want divided by the measure of this, mu of the same set, okay? Mu of the same set. I can write it. Omega such that phi minus lambda less than epsilon. Okay, this is Gn. Then norm Gn 2 equal to 1, and phi minus lambda, you just multiply phi minus lambda Gn, you take its L2 norm, okay, multiply it by that norm 2, that should go to 0.
So in the definition, so like in the definition of Gn, like in the denominator, there should be square root, right? For the mu of
Square root, correct. Yeah, that's the square root. Correct. Yeah, so I just want to make it norm 1. So there's a square root. Now phi minus lambda Gn norm 2, this should go to 0. And sorry, you should take it 1 by n. Sorry. This is not equal to 0. This is strictly greater than 0, so you can divide, and this is less than 1 by n. You just take. Then this will, then this should go to 0, because this is just you have to integrate basically. This square is just you take the integral. The one integral, it will be smaller than 1 by n times something which is norm 1, so that will be less than 1 by n. What is that? Oh, this is, I'm just multiplying by 1. So this so this is just the integral over just this set omega, because I'm multiplying by the indicator function of this, the characteristic function of this. So this is just phi minus lambda less than 1 by n. It is just the integral is over that, okay, of phi minus lambda square Gn square. So this you can just, this is, since this is less than or equal to 1 by n, so this is just 1 by n. This is less than or equal to 1 by n. And that goes to 0. Okay, so the claim, hence the claim. I hope this is fine. Hence the claim. Okay. So we proved our claim that if lambda mu, if this is greater than 0, then that is less than that. So now we want to prove that the supremum, the supremum of so claim implies supremum of lambda in lambda, supremum all those lambdas. That's what we want to see. Okay, and supremum of all those lambdas are precisely the norm phi infinity. That's what I want to say. Yeah, that is the. Shall I leave it as an assignment? Okay. This is just a supremum. Even this I should have left it as assignment. So I leave this as a claim implies norm of supremum of. So this is assignment. Okay. You assume that claim and then you prove this. Assignment is supremum of lambda such that supremum of r of that sigma r of the pi. Is equal to norm phi. But since pi, this is normal operator, the spectral radius and the norm. So, this is assignment. Then this implies norm of pi into phi is same as pi infinity. Okay. You just apply the definition and you will get that. Okay. So you please do this. Okay. I think it's an easy exercise and you can do it. Okay. So we have just proved that this is isometric. Okay. This is we have proved that. So we proved that this is a representation and this is an isometric representation. The norm coincides. And we want to prove this convergence property. Okay, the convergence property is suppose, but that is just Lebesgue dominated convergence theorem. Okay. So suppose, since this is a finite measure, so suppose phi n contained in L infinity such that phi n infinity supremum is less than infinity. This is just a number m, and then this constant function is integrable. Okay, so all these functions are, this is integrable. Then you have to apply that. Then phi n g, and suppose phi n converges and phi n converges to phi mu almost everywhere. Okay, then phi n g minus phi g, this square integral. Okay, this converges to 0 by law of LDCT. Okay, phi n g, integral phi n g converges to that, and it's clear. This goes to 0 by LDCT because they are all bounded by. You can take that norm phi infinity plus norm m kind of thing. It's clear. This is just LDCT. Because of that, this follows. Okay, so one thing I forgot to write is the uniqueness of this. There exists representation. Maybe I should change the whole thing. There exists a unique reason such that this happens. Okay, this extension is unique. So only the uniqueness we have to prove. Okay, we have proved. This is clearly a representation, and we have proved that it is isometric. Okay, I hope the proof is clear. If it's not clear, you ask me. And we proved that the strong convergence property is just dominated convergence. So that's also clear. Because it's finite measure. Okay. and everything is bounded by the constant function. So that gives the uniform bound, and by it's dominated by the constant function. So it follows from dominated convergence theorem. And then we only have to prove the uniqueness. Okay. To prove the uniqueness, it's enough to prove that, so to prove uniqueness, it is enough to prove. And it's clear, the C of x is also multiplication representation. This is also multiplication representation. And C of x is contained in L infinity. So pi mu tilde restricted to C of x is pi mu. Okay, that is clear. Because it is just we are just defining it as a multiplication representation. To prove uniqueness, it is enough to prove there exists Fn contained in C of x. To prove for any phi in L infinity, there exists a Fn contained in this such that Fn converges to phi mu almost everywhere. Right? This is enough to prove this. Then pi mu of, since then the proof is then pi mu of Fn, pi mu tilde of Fn, which is same as pi mu of Fn. So pi mu tilde of Fn, which is same as pi mu of Fn, will converge to pi mu tilde phi. That's what we have proved. But then it has to be unique. Because that is one such representation. You can't have two different. This implies that it's unique. Okay. So we only have to prove this. So to prove that, now it's just measure theory. We want to prove that given any L infinity function, you have continuous function converging almost everywhere. I think we haven't proved. We proved some Lucin's theorem. So, this is also proved with norm of Fn supremum n. It's uniformly bounded also. Supremum of Fn infinity is less than infinity. We have to prove that the norm is also uniformly bounded and it converges almost everywhere. So to prove this, so we will prove this. Okay. So given any L infinity function, we have continuous functions which are uniformly bounded, and it converges to that phi in almost everywhere. Okay. So to prove that, let us discuss some new idea. We haven't discussed in the measure theory course. So we want to discuss something called convergence in measure. Actually, in this theorem itself, you can replace almost everywhere convergence by convergence in measure. Almost everywhere convergence is something stronger than convergence in measure, which I am going to define. So definition. So this we can define for any measure space, but we consider finite measure space. Okay. So X plus mu is a measure space. Okay. Then we say some function Fn converges to F in mu, okay, in measure mu. And we write it like this, in measure mu. If for all epsilon greater than 0, this set, mu of measure of this set, mu of all those omega, all those x, Fnx minus f of x greater than or equal to epsilon goes to 0. Okay. There is something different from what we have done. So this is what convergence in measure means. Okay. So let us prove a proposition. As I said, we can replace the whole mu almost everywhere by convergence in measure in the theorem itself, because that's what we will get. We will get functions. When we have an L infinity function, we will get continuous function which converges to that L infinity function in measure. But then this proposition will say if you have any sequence of functions converging in measure, there is a subsequence which converges almost everywhere for a finite measure. Okay. So from that it will follow that there actually exists there actually exists continuous function which converges mu almost everywhere. Okay. So This is the theorem we want to prove. Mu be a finite measure. And if Fn, then Fn converges to F in measure mu, implies there exists a subsequence Fnk converges to F mu almost everywhere. Okay? I mean, if something converges in in LP or L2, then there exists a. I think we proved that, or I don't remember. It was asked in the exam. It is part of something. Okay, it's part of proving that it's a Banach space. If you want to prove LP is a Banach space, then that proof involves some tail sequence. So if you use that, you will get that if something converges in L2, then then there is a subsequence. It converges almost everywhere. When it is a finite measure, this is also true. Something Fn converges to F in measure, then there is a subsequence which converges almost everywhere. Mu almost everywhere. Proof. So we have convergence in measure. Okay. So choose nk such that mu of this set, mu x, this x such that fnk minus f okay minus let's take greater than 1 by nk 1 by k. So this goes to 0. Okay, I mean this for any, if you fix a k and if you write this n here, then this goes to 0. So I want to choose a nk. I mean, if you have just n here, then this goes to 0. Okay, so I choose a nk so that this is less than or equal to 1 by 2 power k. So this is possible. Okay, because it converges in measure, this is possible. Okay, and we want to prove that this fnk is the sequence which converges almost everywhere. Okay. So to prove convergence almost everywhere, we have to find a set of measure 0. And outside that set, it's the point-wise convergence should happen. So it should converge point-wise outside that set. So we want to get a set. So let AK be this set. AK equal to this set. X such that f and k x minus f of x is greater than 1 by k. This is that AK. The set is AK. And this set has measure less than 1 by k. Okay. So union of AK, k equal to n, k equal to some n to infinity. N to infinity. Okay. This goes to 0 as n goes to infinity. Because this, I mean, this is a sum mu of this. Right? Because this is less than or equal to summation mu of AK, k equal to n to infinity, and this goes to 0 because that sum that's 1 by, this is equal to, this is less than or equal to summation 1 by 2k, k equal to n to infinity. This goes to 0. Okay? As n goes to infinity. This is the tail of that convergent series, so it goes to 0. Okay, so this goes to 0, and union of k. This is the lim sub we talked earlier. This is, I mean, this is something that we discussed, something called Borel-Cantelli lemma in the very first class. Okay, this is something related to that. This proof. Whatever the set I'm getting, it's actually the lim sub. When you have something convergence, the measure of something convergent, then the lim sub, mu of that lim sub is 0. So that's what I'm using. I'm just writing the proof. So then k equal to n to infinity ak. Okay. This set decreases. Yeah, this is a decreasing sequence, right? Because it's union, so it's decreasing sequence. So, and it goes to 0. mu of this goes to 0. That's what I have written. So that implies, this implies intersection, because the measure is finite. Intersection of n equal to 1 to infinity, union of, this is the lim suit, okay, k equal to infinity, ak, mu of this, you call this set as a, is 0. Okay, this is just the limit of that. This, because I mean, this is a decreasing sequence, and the limit is, I mean, because it's a finite measure, this is just the measure is just the limit of that, and that is equal to 0. Okay, so these things we have done in the measure theory. So this is equal to 0. So our claim is outside this set A, when x is in A complement, then the convergence happens. So if x is in A complement, that is x is in that union of k equal to n to infinity ak for some n, okay, n not to infinity complement for some n naught, right? I mean, x is in A complement, so this is the complement of this. That means it's the union of that. Okay, the union of those individual complement. I mean, union of the each complement. So from that, I mean, it's in one of those sets. Okay, so there exists a n naught such that x is in that. Okay, so that is x is in intersection of k equal to n naught to infinity ak complement. But what is the definition? That just says that f and k. You just write the definition. Mod of f and k of x minus f of x is less than 1 by k. Okay? So this implies f and k goes to, this implies f and k goes to f. Okay. So convergence in measure implies there is a subsequence which converges almost everywhere. Okay. It's just I want to do last year itself. I forgot. Last semester itself I forgot. So I'm doing it. Okay. Okay. Anyway, we are using it. Now the next proposition is phi is in L infinity of C with respect to some finite measure. Let's say some C with respect to some mu finite. I mean, we want to consider the spectrum of something contained in this, which is finite. So let us consider, I mean, we can take outside that finite compact set, the measure to be 0, and you can consider measure something is in, I mean, the measure is defined on the pole of C. Then there exists continuous Fn, okay, such that norm Fn infinity supreme is less than infinity, and Fn converges to phi in measure in, okay, that's what we write. So once we prove this, Fn converges to phi in measure, then it follows that there is a subsequence which converges. That subsequence which converges almost everywhere. So then our theorem is proved. Our theorem, we want to prove that pi mu tilde is unique. Pi mu tilde is unique extension. Okay. So there exists continuous function, sequence of continuous function which converges to, given a L infinity function, there exists a sequence of continuous function which converges to that L infinity function. So, I mean, which is uniformly bounded. Continuous function converges to that L infinity function in almost everywhere. So that implies that pi mu tilde of that Fn converges to that, which is same as pi mu of that for continuous function. So then that proves that pi mu tilde is unique extension of pi mu. Okay, is that clear? Okay, you have to tell me whether it is clear. Okay. Anyone has a problem? then I'm bit. I didn't sleep well, so I am bit not a bit of not able to say. Can't. I mean, if it is not clear, you tell me. Okay.
It is fine, sir.
Okay, to find everyone.
Yeah.
Okay. Okay. So suppose, so I have to only prove this proposition. Okay. Suppose phi is in L infinity, then there exists continuous function such that this happens. So this just follows from what was done in the last semester. I didn't do. I mean, that postdoc guy proved. What is his name? I don't know. Okay. So it's Lucian's theorem. By Lucian's theorem, Lucian's theorem is for Rk. I think it's proved for Rn. Okay, but then it's true for C. Okay, so C is like R2. Okay, so by Lucian's theorem, given epsilon greater than 0, there exists a function f continuous. Okay. Given, I mean, given phi in L infinity C with respect to that mu. Okay. Given if L infinity function and epsilon greater than 0, there exists a continuous function such that mu of all those z such that f of z is not equal to that phi of z. This measure is less than epsilon. This is what is Lucian's theorem says. Okay? You can get this. This itself will follow. This is, I mean, we only have to. So we get a I mean, then by taking epsilon equal to 1 by n, we get a sequence of function fn. Then one can check that the fn will go to this phi in measure. It's enough to prove it goes in measure. But then we want that to be uniformly bounded. So for that reason, we have to define a G. Maybe you call this G. For that, we want to get a new function. We want to get a F so that it's uniformly bounded. Okay. Now you define. Yeah. So define another function R. R of Z equal to Z if mod Z is less than norm phi infinity. Okay. Is equal to just mod phi infinity itself. Phi infinity times Z by mod Z, okay, which is a modulus 1. Okay. Then, I mean, this is a radial function and this is a continuous function. Then define f of Z equal to R of G of Z. Okay. Then f is continuous. Check that f is continuous. Okay. It's clear. It's continuous function. That's why I'm defining it like this. Okay. Okay, f is continuous, and then what happens? Then mu of Z such that f of Z not equal to phi of Z. So f of Z is equal to g of Z. Okay, when f of Z, I mean, because R of Z equal to Z, f is just R composed with g. So f of Z is equal to, notice f of Z is equal to g of Z if mod of f of Z is less than phi infinity, non phi infinity. Okay. So, but then f of Z can go, I mean, g of Z can be, I mean, the mod of phi of Z is, so sorry, f of Z is always smaller than that, g of Z. G of Z is yeah, g of Z is, yeah, g of Z is greater than non phi infinity, less than 1. But then g of z can be greater than phi infinity. Okay. And there also it can be equal to phi of z. But wherever that phi of z is equal to phi of z, there the phi of z, that set is 0. This is contained, this is less than, I mean, this set, let us take this set. This set is contained in all z such that g of z is not equal to phi of z. G of z equal to f of z. Okay, wherever that happens, union z such that mod g of z is greater than norm phi. Okay, right? Because when g of z less than or equal to norm phi infinity, g of z is equal to f of z. Okay, so it is having, we don't even need this. Okay? This is equal to that. Sorry. G of z equal to phi of z. Okay. Not equal. Union this. But this set has measured 0. So this set has less than epsilon. So this is less than epsilon. Measure of this. This implies measure of mu of this f not equal to z, f not equal to phi. Okay. But from this it's clear. I mean, choose fn such that mu of fn not equal to phi is less than 1 by n. Okay. Then mu of fn minus phi greater than or equal to 1 by n. Greater than or equal to, I mean, you want to choose it for all epsilon. Greater than epsilon. Epsilon, I mean, this is greater than or equal to epsilon. So this is less than 1 by n, which goes to 0. I mean, this is not equal to phi itself is less than 0. So greater than or equal to epsilon is certainly contained in that. So that is less than 1 by n. Okay? So this goes to 0. So this implies fn converges to phi. So given any L infinity function, we have found continuous functions which are uniformly bounded, and the norm of f infinity is supremum n is less than infinity. We have found functions which are uniformly bounded, and fn converges to phi in measure mu. So this gives a subsequence of continuous function which converges to that in measure mu. Then that implies the pi mu, the representation converges to that, which implies the pi mu tilde extension is unique. Okay. I hope it's clear. The whole thing is clear. Okay. Now we move on to something else. How much time I have? So I have only 15 more minutes. So I will just prove one more theorem, which is basically Zorn's lemma, and then stop. So this is the proposition. So Zorn's lemma is just says that, I mean, you can, if you have any Zorn's lemma assures us that if you have any representation that can be written as direct sum of cyclic representation. We have proved that, I mean, we have proved if it's a cyclic representation, then that is given by a measure. Okay. Then Zorn's lemma will imply that any representation can be written as direct sum of cyclic representation. Maybe the direct sum is infinite direct sum. Okay. Then that implies that you can write it as the direct sum of pi mu n for some sequence, I mean, for some sequence of measure mu n. So before that, let me, since I didn't define it in the last course properly, let me define what is the direct sum of Hilbert spaces. So Hn be Hilbert spaces, sequence of Hilbert spaces. Then direct sum Hn, n in n. I mean, this can be finite. Finite, there is no problem. Okay, for infinite direction, you have to write this. Infinite direction Hn is all those sequence. So Xn, you just write the tuple like this, X tuple or sequence, whatever you take it, such that summation norm Xn square is finite. So it is just taking L2 of Xn with each Xn in n with Xn in. You take such sequences, Xn with Xn in Hn, and then some such that it's a square sum. Okay, so that is what. And then you define any Xn, Yn. This is the same as the, I mean, if you restrict to the finite direct sum case, it's the same thing. You just add the inner product. If you take the direct sum of Hilbert space, then you just add the inner product, and the norm is square norm. The norm of any, I mean, norm of the tuple x1 up to xn is summation norm xn square, the square root of that. Okay? This is just equal to summation inner product xn. Okay? So it's clear because by the usual, this Cauchy-Schwarz inequality for a small L2, from that it follows that, I mean, this check. I don't want to give it as an assignment, it's clear. Okay? Check direct sum Hn is a Hilbert space. But all we have to check, I mean, this is same as the proof of L2 is a Hilbert space. It's a, I mean, it's very similar to that. Okay? You have to, I mean, this is clearly an inner product. And then, I mean, it's clearly complete. I mean, the completion, the proof is, should I give it as an assignment? I think it's not necessary. I think it's exercise. If you have any doubt, you tell me, okay? Well, I mean, if I had, maybe last year I should have given it assignment. I believe this year, I mean, last semester I should have done. I think this should be clear, okay? So this is just a Hilbert space. This is clearly a Hilbert space, okay? Now you can define operator. An operator will be a kind of infinite matrix where each one is a operator from Hn to Hm or something. You can write it like that. But then there is a particular kind of operator which is direct sum of operators you can write. Okay, so we say let Tn for Tn in B of Hn. Okay, write direct sum of Tn. This is an operator. This is an operator. N in N. Okay. This is an operator acting on any direct sum of Xn. Okay, for define Tn Xn. This is just direct sum of, you just component wise you act it. Okay. So this direct sum Tn, n in n, is bounded. This you can define it like this. You can write an operator like this, but then it has to make sense, and it's a bounded operator. Okay. I mean, you can define it on. You can take finite direct sum. See, this direct sum is just the completion of finite direct sum. Or you can see, you need not even define like this. You can define the direct sum. You can alternatively you can define this Hn, n in n, as you just take the finite direct sum. You just take the, I mean, you just take these kind of elements. Direct sum, finite direct sum. Okay? Finite direct sum of xk. And then you can define an inner product between them, whichever is the bigger. Then you can define an inner product that gives an inner product space. I mean, what I'm saying is this is without the completion. I mean, let me not write it because unnecessarily I need to introduce a lot of notation. What I'm saying is, if you have a sequence of Hilbert spaces, then you can take finite direct sum. Just formally you write finite direct sum. Okay, then you can define the inner product on those kind of vectors. Formally you can write it. Okay, so that is an inner product space. Then you complete that inner product space and this Hn direct sum Hn are same as inner product. I mean, the same means there is a unitary between them. Okay, and I think this you should be matured enough to do this. So I don't want to give this as an assignment. So on
I
that
think this was an assignment.
was an assignment. I gave something about yeah, there was
No, that was for Banach spaces. This is
there's a
3D
Banach
spaces.
space, but it's
Oh, okay.
similar to that. It's the same thing, correct?
Yeah, Banach space is a generalization. Okay.
Yeah. So it's very dynamic. It's very similar to that, correct? Yeah. Okay. So what I'm saying is you can define a direct sum like this. So you can define a direct sum Tn, which you can act on finite direct sum, which is well defined. But then you can extend to the infinite direct sum if and only if it's bounded. So it is bounded. This is bounded if and only if is equivalent to saying norm Tn, the supremum of this Tn is finite. Okay. This is like a diagonal matrix, infinite diagonal matrix. And then this is bounded if and only if norm supremum. So this I give it as an assignment. Okay, this is such a small thing. So I give it as an assignment. Okay. This is all right with you that I give it as an assignment. This is easy. Okay. You have to, so I mean, one way is clear. If it is bounded, then you can prove that you can take the coordinate vectors, and on that it has to be bounded. So the supremum will be bounded. Coordinate vectors, you can take unit vectors, and then that will be bounded clearly. On the other way, if this is bounded, then that gives a thing you have to prove, and that's also you can prove. I mean, you can prove that it is bounded on the finite vectors. Okay, so then that will imply that it's bounded. It's very easy. You just formally write it. I just want to make sure that you just write it once. Okay, so that's why I give it as an assignment. It will take few lines to prove this. Okay, so this is about direct sum. You can talk about infinite direct sum. That's what I want to say. Okay. If I have time, I will define inner product and infinite tensor product, and I talk. See, this is like in the category of Hilbert space, you are taking sum. This is direct sum. You can define a product also, something called tensor product. There also you can define infinite tensor product, another thing. Maybe if we have time, we will discuss it later. Okay, after spectral theorem and other things. Okay. So what do we want to do? So all this is I'm doing because I want to prove this proposition. I have 10 minutes, so prove this proposition. So let pi from, I want to talk about C of x to P of h is a representation. By representation, I always means is unital star representation with h separable here. Here we have to assume h is separable. Okay. I mean, if we take our usual cyclic representation, which is given by a measure, then it is automatically separable. But here we have to assume that it's separable. With h separable, then there exists a countable collection of mu n. It can be finite also, okay? But it can be at the most it's countable. Mu n such that n in n, such that pi is unitarily equivalent to direct sum of n in n pi in n. Okay. What does it mean? That is pi of any f is unitarily equivalent. There exists a unitary. There exists a unitary u from h to direct sum of L2 mu n, okay, such that this pi of f looks like pi mu n of f, direct sum. Okay. That's all. Okay, so that is what you want to prove. The proof is just this answer. Okay, what do you want to prove? So the reason is anything can be written as, I mean, this Zan's lemma says that representation, since h is separable, that representation pi can be written as direct sum of cyclic representation. And then we know each cyclic representation is given by a measure. So from that it follows. Okay. So there exists. So So we say the following. We say, yeah, H naught contained in H is a Hilbert space, closed subspace. It's a Hilbert space, is invariant for pi if pi f of H naught is contained in H naught. Okay. So then we say it's invariant. So since f bar is also in, this is for all f in C of x. Okay. Since f is there, f bar is also in C of x. So, I mean, this will imply that pi of f bar is equal to pi star of f. Okay. This is invariant under star also. If pi of f is invariant under that, it's invariant under star also. So something is invariant under f and f bar, then the, I mean, this you know from linear algebra, I believe. Then the star, I mean, which you can directly, you just write it, it will be clear. Okay. This is, we didn't do it, I believe, but this implies exercise. Pi of f, the perp, H naught perp is also contained in H naught perp. Okay. I mean, you use the property of that joint. If something, if m is x is, sorry, H naught is invariant under some operator t, then H naught perp is invariant under t star. Okay. You just write the definition of star and write the whole thing, you will get it. Okay. And use the fact that H naught perp is H naught or whatever. Okay. This is an exercise. Okay. You just write the definition, you will get it. Okay, so pi of f H naught is contained in H naught. So this implies that you can write that representation. Then you can write. So this means this pi equal to pi restricted to. You can restrict to this H naught. I mean, as operators, you can restrict to H naught, and pi restrict to H naught perp. You can write it like this. I mean, this I think it's clear what I mean by this. Okay. You can write that. I mean, you can write H as direct sum of H naught and H naught perp, and pi restrict to H naught, and pi restrict to H naught perp. So you can write every operator pi of f as direct sum of pi of f restricted to H naught, pi of f restricted to H naught perp. Okay. It's just the direct sum. I mean, it just means that that operator does not take any element from H naught to H naught perp. It just look like this. Pi of f, pi of f. If you write it as a matrix, okay, this just looks like this. Any operator on H can be written as a matrix like this. H naught and H naught perp. You can write it with 4 operators. You can write it like that. This is an operator. I mean, here whatever the off diagonal elements are operated from H naught to H naught perp and H naught perp to H naught. You can write it as a matrix like this. These elements are 0. That's what it means. You can write it as a diagonal matrix like this. Okay. So we want to say the whole representation can be written as the diagonal matrix with respect to that infinite direct sum. That's what I want to say. Okay. So, but then that is just John's line. Okay. Now, so I mean, this is now consider the collection. Collection Hn. No, the point is this. So you can take any vector. Okay, take any vector, take any xi, okay, and consider H naught. H naught. I mean, this is an. I mean, if so, here I have said that if any H naught is invariant with respect to for this pi, then the H naught perp is also invariant. Now you take a particular H naught for any xi. You define H naught to be pi of f. You take xi naught. Then you take this span closure. Span closure of this. Call this as H naught. H naught. Then H naught is invariant. That is just clear. Pi of H naught is contained in H naught. If you just apply on this dense set of vectors, then it is just pi of f. I mean, if you apply some phi of g, then that's just going to be the product on that pi of gf or something, which is again in. So it's clearly H naught is clearly invariant for this. Okay, that is clear. So there exists one such element in the following collection. This implies now, now consider the collection. Consider the collection. I don't want to go through the Zahns lemma argument, which is standard. We have done it several times. Consider the collection Hn, okay, and Xi n. You consider this collection where with you consider the where Hn is orthogonal to Hn if n not equal to n, and pi and Xi n is cyclic for this. Xi n is in Hn and is cyclic. For pi restricted to this Hn. Okay, you just take orthogonal collection H1, H2 up to Hn or whatever. You take the collection Hn with Xi n cyclic vector, so that this pi restricted to that is cyclic. We know that there exists one single element in this. It's not an empty set. Okay. Then we have Hn is orthogonal to Hn. Okay. So by Zahns lemma, there exists a maximal. then you include it. This is just a set. Hn is a smaller set. You consider the bigger set is H1 up to Hm or something, where this H1 up to Hn is contained in that. Okay, this thing, you know how to do it. Okay, by Zahns lemma, there exists maximal element. There exists, Hn Xi n, this collection with n in n or whatever. The Hn is orthogonal to Hn. This cannot be an uncountable collection. This has to be countable collection. Okay, H is an Hilbert space. It's a severable Hilbert space. So the orthonormal basis itself is countable. So you cannot have orthogonal subspaces which are uncountable. Okay, it has to be countable. Okay, so otherwise there will be an uncountable orthonormal basis, which is not true. So this has to be a countable collection. So there exists Hn Xi n such that this is a maximal element. Maximal element means there does not exist a bigger collection than this. Okay. Then the claim is, then it's clear. The claim is direct sum of Hn equal to H. If not, take H not equal to direct sum of Hn. Well, and since this is invariant, that has to be invariant. You can add that, and that is a bigger collection. So it is clear that that has to be maximal collection. Okay. Now each Hn pi restricted to Hn is unitarily equivalent to pi mu n for some mu n, right? Because that's a cyclic representation. We proved that any cyclic representation is unitarily equivalent to mu n. Okay, so there exists unitary. There exists un from Hn to L2 mu n, such that un pi restricted to Hn, okay, pi restricted to Hn un star is equal to that pi mu n. Okay. Now pi, which is equal to direct sum of pi restricted to Hn, okay, is unitarily equivalent to direct sum of pi mu n. To take this, this is given by the direct sum of un. Since each un is, we just discussed some time back. If you have a collection of bounded operators, then you can talk about the direct sum of bounded operators if the supremum of the norm of that un is finite. But these are all unitary, so norm of un equal to 1. So you can talk about the direct sum of unitaries. So that direct sum will give the, that will intertwine this pi restricted to h into pi mu, direct sum of pi. So we proved our proposition. Our proposition is every representation is given by direct sum of this pi mu. Okay, that's what you have. So if you have any doubt, you ask me.
So like, why do we care about this representation?
Why do we care about this pi mu? We want to prove spectral theorem. That's all. Or, this gives another thing. This gives a classification of all representation of pi of x. No, pi is some arbitrary. See, we want to study representation of pi of x, which is we want to study the C-star algebra C of x, which is a commutative C-star algebra. Okay, and there is a theorem says that all commutative C-star algebra will look like this. Now you are just classifying all representation of this. Okay, every representation of this. This is what is called Hellinger Theorem kind of thing. Okay, that is slightly more general, but this is that all any representation of C of x will look like this. If you want to study representation of this, that is mathematics is some sort of study. You study objects and study its representation. Okay, C of x is something and how it acts on Hilbert space. This is even if you see there is a study of groups. When you want to study groups, you represent it on Hilbert space. If you have finite group, then it is enough to represent it on finite dimensional spaces. That is enough. Okay, that study will give all representation. Even if it is infinite, you can write it as direct sum of finite representation. So that is, you can actually write it as irreducible, and this is like irreducible. If you know something about representation of groups, the cyclic representation is some sort of irreducible representation. Okay, there is some sort of irreducibility. That's what the cyclic thing. Now you are saying that every representation can be written as direct sum of irreducible representation. That is one thing. And every irreducible representation, which is the cyclic representation, is actually given by a measure. Okay. So you just classified all representation of C of x, a particular kind of algebra. So that's why we study. And here our purpose is to prove spectral theorem. Okay. I will stop recording and I will say something. I will announce something.